specifically for historic structures, projects utilizing his experience in seismic expertise, including earthquake damage and/or vulnerability assessments and repair for numerous structures, including the Washington National Monument, the Washington National Cathedral, San Francisco and Oakland City Halls, to name just a few, as well as the seismic strengthening of notable historic buildings in San Francisco, including two pre-1906 buildings by Albert. I asked him how do I say the last name, and now I've forgotten how he said it. Piers. Thank you. I can't. Sorry. Okay. So also, Terry has been the recipient of a variety of awards for his research and practice, including the Mosef Award, the ISD Presidential Award for Excellence in Structural Engineering, and the 2006 ASCE Region Award Seismic Retrofit of the Year. Terry. I didn't say all your things. There was a lot. There's.
Good morning, everybody. So I'm going to be talking about how the structural provisions of the CHBC can help a project pencil out. I'm not going to read through all these bullets. They're also in your program. That's exactly how I'm going to address the global subject. I will tell you at the outset, I will admit that I don't have a particularly prescient set of messages for you today, because I think that the messages are pretty obvious. These aren't things that I've invented. These are strategies for achieving success in seismic projects and historic buildings that involve different ways of making things less expensive. It should be very clear from the outset that the more structural intervention that we do on historic buildings, the more stuff's going to cost, the less likely it's going to be to pencil out. So the practical reality is that we should target all our energy on figuring out how to reduce the level of structural intervention that's required. And luckily, the CHBC gives us lots of ways to do that. I will tell you that as part of that, we need to all understand that the entire preservation community needs to understand that preservation is not subordinate to seismic safety. It's often taken to be subordinate on real life projects. I mean, we see it all the time, but it's not subordinate. The reality is they're equal partners in things. And the reality is that engineering for seismic safety, there's an interaction between seismic safety and preservation. You know, just even in the engineers' quarters, where there ought to be an interaction, there needs to be kind of a handshake between the two, and I think unfortunately there isn't. In any case, kind of the strategies that we implement on our projects include this: supplement but don't supplant, right? The idea is not to replace historic structure, it's to supplement it, because historic structure has a lot of value in and of itself, structurally as well as historically. I've mentioned this before, but kind of shorthand notion, the more disruption you do, you'll start your project out essentially in a deficit position. So you need to limit the amount of disruption. Disruption occurs both because, I mean, for a lot of reasons, but again, the more structure that you try and install in a historic building, the more disruption you're going to have. I'm going to use three different projects of ours as case studies throughout this presentation. This one is Congregation Cherith Israel in San Francisco. It's a 1904 unreinforced masonry bearing wall building. Without reading to you all its merits, I will point out that the image on the left could have been taken both before or after the work we did. We didn't touch this. Anything you see in this image was really not touched during the seismic upgrade. This building is now compliant with city requirements. There are ways to make this work in real life. Also, Hibernia Bank building, both these projects, by the way, are just completing right now. Hibernia Bank building, again, the image on the left could have been taken either before or after the seismic strengthening work. Both these buildings, you know, something like 70% of the volume of the building is included in these giant halls in the sanctuary in Cherith Israel. We stayed out of those areas, and as a result, these projects work. They were successful from beginning to end, and they were cost effective. Now, the Washington Monument, similar in a different sense, is not subject to the CHBC, obviously, but there are certain things that we did on this project that I think are relevant and can be done in the CHBC, and so I'll mention those as we go along. Okay, look, a few things about the CHBC structural provisions. There's going to be a little overlap here between myself and Alan, but I'll try and kind of pop through those things pretty quickly. On the first slide is really, tells you that where the structural provisions live in chapters 1, 2, 7, and 8, or at least the structural requirements. What's important here is, as Alan said, to understand how to read the CHBC. It's not our job to go fishing around in the CHBC looking for requirements that appear to apply to our project. That's not how it works. You start in chapter 1 and figure out where chapter 1 directs you for the project that you're involved in. If you fish around and look at, try and pull out those provisions that appear to be applicable, you're going to be doing more work on your building than you actually have to do, because there are things in there that appear to be applicable to lots of projects but aren't. So start at chapter 1 always and look for the charging language, which in some places is obviously absent. Which is interesting. But okay, so structural repairs, I think Alan already mentioned this. You can make them in kind. I mean, that's it. You have a structural repair project, in a historic building. You can make them in kind. You are not required in any way to go to chapter 7, in which the structural regulations reside in the CHBC. Unsafe conditions, Alan already mentioned as well. Again, it's important to understand two things, and I will emphasize Alan's point because I think it's a great one. Don't let engineers tell you, or building officials tell you, that buildings are unsafe under the code because they don't comply with the seismic requirements of the code. That does not make a building unsafe. In any case, again, with respect to unsafe conditions, you can just remediate those unsafe conditions and you do not have to go to chapter 7 of the CHBC. Voluntary strengthening is also a fascinating part of our CHBC. There is actually, it's important to note that just because you're doing voluntary strengthening, again, you don't end up in chapter 7 in the structural regulations. There's no path to chapter 7 in chapter 1. It's very clear, however, that the code does say that nothing in these regulations shall prevent voluntary and partial seismic upgrades when it is demonstrated that such upgrades will improve life safety and when a full upgrade would not otherwise be required. The point to that provision, and in keeping with kind of the general philosophy that we use in these projects, is that if we target critical vulnerabilities in historic buildings when we're looking to seismically strengthen them, and we limit ourselves to critical vulnerabilities, we can save a heck of a lot of money, we can reduce a heck of a lot of intervention, and the code explicitly allows us to do that, right? On a voluntary basis, when we're involved in a voluntary strengthening project, we don't have to do everything. If we can solve 80% of the problem for 20% of the money, why wouldn't you just do that and stop there? So anyway, it's an important lesson. The code allows us to do that. With respect to change in use, as you probably are aware, many people consider change of use as a trigger for upgrading buildings. It is a trigger in the CBC, but it's not a trigger in the CHBC. Additions, similarly, I think the lesson with additions, if you read these provisions, is that try and keep your addition structurally separate from the historic structure, because if it's touching it and it either takes load from it or adds load to it, you wind up with all sorts of problems. So again, the language is pretty clear in the code, and I think the lesson from it is pretty clear. If you need to make an addition, keep it structurally separated. Mandatory strengthening is where I actually wish the CHBC were slightly had better language in it. But understand that the motherhood language so mandatory strengthening, you have to go to Chapter 7. Really, there's no other place to go in the code, even though the code doesn't actually say you have to go to Chapter 7. We infer that you have to go to Chapter 7 because there's really no other way to interpret it. But Chapter 7 clearly says that the intent of the chapter is to encourage preservation with the objective of preventing partial or total structural collapse, such as the overall risk of life-threatening injury as a result of structural collapse is low. So again, it's kind of focusing us on this notion of structural collapse. It's not asking us that we look at every little item in the building that might fall down. It's not saying you shall prevent all brick fall. It says you shall, essentially what this means to me is you shall prevent structural collapse such that say walls collapse and floors thereafter collapse. Not local brick fall. That's not really, that's not on our radar. In any case, the CHBC allows us to reduce design forces from the standard code to 0.75 times the forces. All right, let's talk about kind of more the heart of the talk, which gets into the capitalizing on inherent strengths of historic buildings. Look, to capitalize on inherent strengths, first of all, the structure must have inherent strength, right? If we have a structure that doesn't have any, is there such a thing? No, I would tell you there's no such thing as a structure that doesn't have inherent strengths. In any case, knowing that every structure has some sorts of inherent strengths, our job is to identify them, quantify them, because as engineers, everything has to be quantified, and to leverage them in the final design. And I'll give you some examples as we go along about leveraging inherent strengths, because you know, you don't always get exactly what you want in a historic building, and certainly some historic buildings have fewer inherent strengths than others. But our job, if we really want to help projects pencil out, is to figure out what they are. Don't give them too little credit, don't give them too much credit, but give them credit. In any case, I will tell you that in order to capitalize on inherent strengths, this last bullet is perhaps the most important. Everyone on the team has to embrace this philosophy, right? If you have one rogue team member, even the municipality, I consider a team member here. They can be either they're with you or they're against you. Everybody has to be committed to the notion that inherent strengths in historic buildings are reusable, that we can use them in a current scheme of seismic resistance. We just have to figure out how much we can use them and where we can use them. But if we decide at the outset to not use them, there goes the project. Okay, so I've already said this. Does the structure, ask the question, does the structure have inherent strength? Yes, there's really nothing else to say. So how do we go about identifying, quantifying, and leveraging the inherent strengths in a historic building? Well, I've itemized a few ways of doing that here that, again, none of these things don't you already know. But I'm going to show you some pretty pictures in the course of explaining them to you, and maybe that'll make it up to you that I'm telling you what you already know using nice pictures. So first of all, talking about archival research. I mean, historic buildings, the older they are, the more historic they are, the more stuff there is out there that can tell us about the buildings. And not just what they were used for, but from the structural perspective, things that engineers actually can leverage if they knew about them. So engineers may not be great at research, right? But somebody's got to do it. You got to figure out who on the project team is going to be charged with that. But historic photos are phenomenal. I will tell you that on Sheriff Israel in this image, the main roof elevation is about 65 feet. The top of that dome is about 120 feet in the air. That's whatever, 55 feet of spindly steel. Impressively spindly, but it works. It went through 1906. It works. It helped us understand, where we didn't have structural drawings, how this thing was put together. We did have a few drawings. On the right is an image of an Albert Pice's architectural drawing. We had a handful of Pisces architectural drawings that kind of showed us where the structure was, but really didn't define the structure very well. On the Washington Monument, archival research, as you might imagine, was, I mean, you could retire doing archival research on the Washington Monument. Just great, great stuff available. The image on the left is a sheet that records the compressive strength of the stone that was used in the monument. I mean, just a ton of really, really cool stuff. This is one of my favorites, but you kind of got to be a geeky engineer to appreciate it. You know, in the old days, engineers, I mean, they didn't have calculators, right? I mean, they could do long division and stuff, but they didn't have calculators, they didn't have computers. Engineering methods were largely graphical. This is one of Lieutenant Colonel Casey's sheets, the design sheet for the Pyramidion on the top of the Washington Monument. And it's really hard to see here, I know. But you can see a bunch of kind of paraboloid type shapes. This is his graphical solution for how the loads get transferred, yet how they get carried in the Pyramidion for wind out of plane. And what's interesting, what I love about it is there's a bunch of notes on here. And if you follow the chain, as all archival research does, you figure out in the notes, well, he's thought about, well, if wind pressures exceed certain amounts, what other means of structural strength do we need? He references certain textbooks. I mean, it's a wonderful piece of documentation that he actually put in here. He references certain textbooks that are still available that we were able to find and reference. So we understood what he thought about the design at the time. And I'll tell you, it goes for Lieutenant Colonel Casey and it goes for Albert Pisces. There were a lot of really smart engineers back then who designed some very, very competent structures without benefit of computers. Yeah. Okay, so a little more about what we can do to establish kind of what our inherent strengths are and quantify them. Obviously, field observation is a huge part of it. You might find yourself in some awkward positions at times, but you can learn a lot. These are images from the Hibernia Bank building. I suspected when we first became involved in that project that the partitions and the like had all been wood framed prior to the earthquake and conflagration. But I had no proof of it because we had absolutely no drawings for Hibernia. But in rooting around in the building, I found burnt timber that I think was part of an old partition. And I think Pisces, see, Sheriff Israel, everything is done in wood also. And I think that Pisces did this building in wood, but made it fireproof after the conflagration by rebuilding all the interiors back in hollow clay tile, which was lovely. So we also found, very interestingly enough, other signs, other marks from the conflagration. These are steel beams in an area that I call the bookend that we'll describe in more detail later if I get to it. Don't talk too slowly. These steel beams are actually warped by the fire. That's our conclusion. The steel beams heated up, they got weak, the material weakened, and they were not allowed, as they expanded, they were not allowed to expand by the masonry walls, and so they buckled. Same thing happened up in the attic. The main roof of Hibernia is supported by steel trusses. What you see in the image here is the bottom cord of one of these steel trusses actually bent. And somebody later came in and infilled the area with concrete to prevent it from buckling further, which is actually quite a clever solution. And we don't know who did it or when. Okay, other things to help you establish what inherent strengths of buildings are: destructive testing. On most of the masonry projects you guys have been involved in, there's probably been a fair amount of testing, in plane shear testing of the masonry. There's a photograph of that stuff in Hibernia. I will tell you that the reason I put in that image in the upper left-hand corner is to underscore the importance of making sure that equipment is calibrated. Too often these testing agencies will come out to your site, do tests, give you numbers that don't make sense, and now you've spent a bunch of money and you have numbers that don't make sense. It's very important to make sure this stuff is calibrated before it takes place. We go to great lengths to use non-destructive testing in our projects where it's applicable. The image in the upper right is of ground penetrating radar. It works, it does wonders on things. I'll just tell you a couple things here, and Sheriff Israel. We were able to locate all the veneer anchors, and the pattern of the veneer anchors. Sheriff Israel, as you saw on the first slide, has a Calusa sandstone veneer. We were able to locate all the veneer anchors and understand whether the veneer was appropriately anchored or not, appropriately supported or not. But perhaps more fun, you see here's an image of a gentleman running a GPR over the cornerstone for Sheriff Israel. There had been a long reported rumor within the congregation that there was a time capsule buried behind the cornerstone. And in concert with the facility, we arranged to go out and do some ground penetrating radar and see if that rumor was true. And lo and behold, it was. And the time capsule was right behind the stone in the area outlined by the orange box. So we measured out really where that was and went to the interior, tore out some of the partitions, yanked out the time capsule, and now they have it, which is pretty cool. And all, not without doing any damage, right? We obviously didn't want to do damage to that cornerstone. Okay, destructive and non-destructive testing in concept. You have to be willing to, sometimes you got to do some damage to stuff, right? And you end up with a matrix of what's the biggest bang for the buck? Where am I going to get the most information for the least damage? So this is the image in the left-hand side of Hibernia. And it's maybe hard to tell, but there are maybe a dozen holes that we've drilled in the interior of that panel. But we picked a piece that is not very decorative and can easily be restored. This particular building was not on the city of San Francisco's unreinforced masonry building list. So we didn't know at the outset of this project, was it unreinforced masonry building? Was there a steel frame hidden somewhere in here? We absolutely had to find out. I mean, this was a key issue in the tree of decision making, right? So we made a bunch of these holes, and we of course discovered that this is an unreinforced masonry building. There is one portion of the building, kind of an internal, a second floor that's supported by cast iron columns, but the bulk of the building is all unreinforced masonry. Don't be scared to drill holes. Sometimes you can get a lot of information from them. Just be careful how you do them. Benchmarking is something that I really want to emphasize for you guys, and it's pretty engineering-y. But the point is to try and figure out is to use the fact that these structures are historic to your advantage. Because they're historic, they've been through a number of loading events, right? They've seen large crowds over time. They've maybe seen earthquakes. They've seen big windstorms. Those loading events can help us quantify what are the structural characteristics of these buildings. How good are they? How bad are they? Where are they most vulnerable? So there are ways of particularly in earthquake land, of leveraging this information. For San Francisco, we have lots of information from the USGS about that helps us characterize what the intensities of ground motions were back in 1906, which for any building that was around that time and went through it, that can give us an awful lot of information, both conceptually and on the analytical side. This is another image that actually Jack Boatwright at the USGS did quite a while ago now, that tracks the intensities of the presumed intensities in San Francisco in 1906. This map, of course, is not strictly ground shaking data. What this is damaged building data. So it a little bit hybridizes, right? It's the concept of, well, if you had really bad construction in one part of town, it might have shown up even though you didn't have super strong shaking as a more highly shaken area, right? So it blends it all together. Anyway, benchmarking, it's benchmarking and archiving kind of go back and forth. Everything's hand in hand. You look at photographs as part of the benchmarking process if you have photographs available. Here's Hibernia. And I just want to point out in the top slide, so this is Hibernia before it was expanded in 1904. Notice this building across the street. On the lower part of the slide, there are two images of Hibernia after the fire and of the neighborhood. And you'll see that the building across the street is down as well. Just keep that in mind for a second. But the images of Hibernia really helped us understand how it worked in 1906. And what we see is that structurally, it really wasn't damaged by the shaking, it was damaged by the fire. lots and lots of fire damage. Photograph after photograph demonstrates that we have this from all sides. We also know from archival research that the building reopened something like 5 weeks after the earthquake. People were able to get their money out, which is pretty good information if you're trying to figure out how earthquake resistant this building is, right? They didn't have, the whole roof didn't collapse inside, you know, hidden damage where nobody could get in and get their money. We found the USGS actually had some descriptive information on what happened to this building after the earthquake. So we utilized that. This is one of the images that I love. This is the backside of Hibernia. And you can see this is after the earthquake, but before the fire, or kind of when the fire is moving. And it appears to me that crowds of people are watching as the fire is moving up the street. You'll notice that this building is the one that I pointed out to you a moment ago. It actually stood up. It was standing after the earthquake. I think, you know, you probably all heard there are lots of debates about how much damage the earthquake did versus how much the fire did. I think this is one of those photographs that suggests the fire did a lot more damage than the earthquake. Okay, Sheriff Israel, same thing. Lovely, lovely pictures shortly after the earthquake. You can see Lane Hospital in the background. Lane Hospital was actually never reopened after the earthquake, which told us, in addition to the mapping information that I showed you previously, that this part of town was significantly shaken. Sheriff Israel was damaged. The gable end walls were damaged. You can see some of the coping stones on the ground and a lot of them missing from that gable. Lots of information in the Bancroft Library on Sheriff Israel, some of it eyewitness records that tells us what was visible from the street at the time. This is all extremely valuable stuff for engineers, right? For if you want the project to utilize inherent strengths, you got to dig this stuff up, or it's just going to be guesswork. And as you probably know, the more you ask engineers to rely on their instinct and not real information or not numbers, the less comfortable they're going to be with saying, yeah, that's pretty good, right? If you want engineers to say, that's pretty good, you got to give them some meat. You got to give them some meat. So, okay, in Sheriff Israel, again, part of the benchmarking process is doing physical investigation. I'm not going to explain structurally to you, but these blue partition walls were actually, there's an image of one of them. That's 1906 earthquake cracking in those partition walls. Sheriff Israel's kind of a museum. They never really repaired an awful lot of the 1906 damage. Same thing up in the drum. These piers all had cracking, extensive cracking in them. What's behind this pier is that some of that really spindly steel that I showed you in that earlier photograph. Damage to another masonry gable end wall in the building. Told us that the masonry gable end walls are quite vulnerable. Okay, here's the only thing I really have on the part I'm going to stress on the Washington Monument. It's important for benchmarking purposes. The reason I put the Washington Monument in here is that for us, this was a zero cost solution, right? Benchmarking enabled us to tell the National Park Service, who is a great client, by the way, that we don't think the tallest unreinforced masonry obelisk in the world is all that seismically vulnerable. So you don't have to do anything to it. You don't have to strengthen it. It was largely on the back of benchmarking that allowed us to tell them that with confidence, right? With comfort. So there were some slight improvements done to the Pyramidion when the repair work was being done, but it was on the thrust of this slide, which I don't think you're really all interested in all the detail, but the black dashed line is essentially the representation of the forces that would be imposed on a building in the maximum considered earthquake. And the purple and blue lines are essentially representations of the forces that were imposed on the monument during the mineral earthquake in 2011. So if it already made it through an earthquake that's more intense, has more force than the design event, why would you strengthen it, right? So we rely a lot on the seismological information. I'm going to skip that one. But essentially, this stuff all goes into, I mean, that was kind of a conceptual look at a plot, but all the stuff goes into computer analysis where we compare what are the stresses in the structure under the event it's already been through versus the stresses in the structure under the event we're supposed to make it good for. And if they're pretty similar, then the engineer has, I mean, this is gold for an engineer, right? And it can turn into gold for the project as a whole if it saves a lot of intervention. So these kinds of analyses can easily be done. You know, you can make lots of pretty pictures with lots of information to try and calibrate your models and show, hey, look, we can actually predict the damage that actually happened, which is exactly what we tried to do in the Washington Monument. We created models, subjected them to the representations of ground motion for the mineral earthquake, and tried to see, hey, are we predicting the damage that actually happened that we're actually able to document? Okay, the last major part of this presentation, how am I doing on time, by the way? Oh, awesome. Because this is a big part. But yeah, that's almost perfect. So capitalizing on the strengths, on the inherent strengths of historic building. Well, look, as I kind of implied before, but didn't say expressly, the CHBC permits rational assessment of seismic capacity. We don't have to adhere to all sorts of published methods. ASCE 41, which you may have heard thrown around a bunch of projects, you don't have to use that. If you use rational methods, you can use them. If you use for engineering first principles, you can use them. You can use things that aren't even all that easy to quantify. I mean, let's look at Hibernia. Here's some images of it. I mean, absolutely massive granite blocks. Massive. And in fact, these column covers are single pieces of granite. There are no horizontal joints in them, as you'll probably notice, but massive blocks of granite. And you'll also notice that the exterior walls of this building is just a bunch of piers and spandrels. There's piers and spandrels, some of them very tall. Well, the reality is that when a building like this tries to sway in an earthquake, and it will sway because all buildings sway in earthquakes. I mean, it may not look like it's swaying, but all buildings sway. When buildings like this sway, those piers want to rock. Just like you're trying to move your refrigerator across your floor in your kitchen and you're pushing a little too high up on it. It wants to tip a little bit. But if you let go, it comes back to its stable position, right? Unless you really, really push it over really far. Pier rocking is a perfectly acceptable means for resisting earthquakes. We are allowed to rely on it. We don't, as engineers, we don't have to say, oh, those piers are rocking. I can't do that. No, pier rocking was indispensable to making the Hibernia Bank building work with minimal disruption. So for your benefit, I'm going to show you exactly how beneficial it was. This is a floor plan of Hibernia, and in red, I show the walls that are brick, or the portions of the walls that are brick. In gray, I show the portions of the walls that are granite. In the north-south direction, which is depicted on the image up and down the sheet, you can see that all those piers and that those rocking piers are responsible for resisting, well, almost 50% of the total required load for upgrading this building and making it compliant today. So there's a couple ways to look at that. If they resist 50% of the required loads, I get to not put in 50% of this new structure that I would otherwise be required to put in. So I can save myself tremendous disruption. If you look in the other direction, those values add up to almost 70%. Almost 70% of the forces required are resisted by existing structure. I mean, how great is that? It's fantastic if you're looking to install less new stuff, if you're looking to do less damage. I'll tell you that, kind of looked at it in reverse, and I don't really always love to do this, but prior to the time that we became involved, there was another engineer on this project. That engineer failed to recognize that pier rocking was an acceptable, at least partial solution to the seismic resistance of the building. And he specified the installation of a ton of really thick shear walls, concrete shear walls, all around the property, in some of them in the positions, the precise positions that I show here. He was going to block a whole bunch of windows. He was going to destroy some of the interior of the banking hall. I mean, this project would have been a disaster. It would have added a lot of cost. And just from the standpoint of of acceptability from the preservation standpoint, just a disaster. So you need to, this is one of these inherent strengths in the buildings that you need to kind of look for and take advantage of. Similarly, in this slide, I'm just simply highlighting that massive granite block masonry is not prone to the same kind of degradation as brick masonry. Brick masonry, every cycle, it really kind of falls, you know, you start to shed bricks, it has some less desirable characteristics to it. But massive granite masonry, I don't think you could shake the stuff apart if you wanted to. I mean, these blocks are massive. We actually took the time to kind of map the general geometries. I mean, some of these blocks are 6, 7 feet long and 2 or 3 feet wide. I mean, how are you going to get those things to slip off each other in any earthquake such that you lose vertical support? I don't think it's possible. Now look, Cherith Israel, a very similar kind of picture. If you look at Cherith Israel from the outside, you see the walls are highly articulated. You see these giant kind of arch shapes out of masonry built into them. Arches, invented by the Etruscans, popularized by the Romans, are one of the most successful structural types of all times. Why wouldn't we try and take advantage of arches in today's construction? They work. These are sound elements. They may need to be supplemented. They may need a little boost, but they're good. They count for something. We need to use them. We need to identify them. We need to use them. How do we do this? How do we creatively leverage these strengths? Well, look, here's an image of Hibernia again. In blue, I show all the areas where there were very significant finishes that really, I mean, no one told us we shouldn't touch that stuff, but you just take one look at it and you say, how can I, in good faith, as an engineer, specify structure within these areas? So guess what we did? Here's where we put our structure. Okay, I just simply, it took a little extra work. It took a little creativity, but you try and locate your structure to the degree you can, and in almost every building, I think you can, depending upon the building's flaws. This one happened to kind of start out pretty good. But there are places to stick structure that do minimal, if any, damage to the interiors. So I'm going to explain to you what we did. So back, if you look up in the top of the sheet at an area that we call the bookend that I've mentioned previously, that area, the walls I'm highlighting are in the north-south direction are actually, they don't contribute strength. They don't contribute stiffness. These are big, massive, heavy walls that, my goodness, you actually need, they need to be supported all by themselves, not to mention the fact that they help to drag the whole building down. There was an easy solution, an easy solution. All we did was stick in these little yellow, what I call web walls, that turned this assembly into a box girder. You know what a box girder is? It's a vertical box girder. These are horizontal box girders. Look at the way these things cantilever off those piers. Well, our vertical box girder cantilevers out of the ground. But this is the analogy. We already had those two red flanges. I show it kind of structurally in our plans at the bottom of the sheet. We already had those two red flanges. All we did was stick in those little walls in a part of the building that that wasn't even rated as particularly significant. The efficiency of box girders is remarkable. I mean, you just look at this image. So that's all we did. It took, I mean, yes, it took some work, but it enabled us to stay out of those significant areas. With respect to Cherith Israel, look, brick masonry can be very, very strong. And in fact, what we found in Cherith Israel, where prior engineers had said it wasn't strong enough and we need to put in a lot of shear walls, we found that the brick masonry all by itself was strong enough. However, brick masonry, as I alluded to before, it's really not all that tough, right? It can start to it degrades in earthquakes fairly rapidly. So we felt that it would be a very good idea to improve its integrity, which we did by center coring. And all these little arrows kind of show you where we put center cores. I presume that most of you know, or some of you know what center cores are. In case you don't, here's an image of some center cores being installed. These are just holes that are drilled from the roof. In this particular case, actually, we did vertical center cores and horizontal center cores, but holes that are drilled from the roof They went down threaded 65 feet, 75 feet down through 3 and 4 white masonry walls. You insert a steel rod in them and you fill it up with grout. In this particular case, we put in Sherath, Israel, we put in over 8,000 lineal feet of cores. I mean, 1.5 miles of cores. We use dry coring so as to not risk damaging those historic plaster finishes inside. And we used a customized mix of polyester grout that actually also has phenomenal properties to it. Here's an image of a center core that we record during the quality control phase. This looks like concrete, but it's not. There's actually a polyester resin. This stuff is phenomenal because it permeates the brick, it permeates the mortar in the area, it bleeds through the whole system and helps, it strengthens it, even though you're not allowed to count officially on that strengthening. It integrates it, which is really what I said we've used this for. It integrates it. Look, in Sherath, Israel, how did we take advantage of these big arches that I showed you an image of? Well, we wanted to hold on to the arch because the arch, you know, one of the big failure modes in unreinforced masonry buildings are the walls falling out. So while I have these big arches in the exterior, I didn't really have too much to stop the walls from falling out. So we put in some very traditional things like floor to wall ties, but also in the roof of the structure in the attic, we put in a tension tie system, such as you've seen in religious and monumental structures all around the world, right? Historic structures. But instead of making it out of steel, or entirely out of steel, and instead of running it right across the sanctuary, we came up with a cute little way of running it around the sanctuary on the outside of all the plaster in the attic space, and use super elastic wires, the first application in the US, to help stabilize these walls, to hold them in case they wanted to fall out. This stuff is actually incredible. But what's more incredible is that now when you go into Sherath Israel and look up, I mean, you don't see our work because it's on the outside of it. It's all on the outside of it. So we did a whole bunch of work up there, but it's up above. Okay, last piece of this puppy. I wanted to talk for just a few minutes about life safety of non-structural components, because I know that non-structural components oftentimes in people's mind drives an awful lot of invention. Even though maybe they shouldn't, strictly speaking, but they do. So let's chat. Ceilings, parapets, and hollow clay tile. Again, just a phenomenal image of Sherath Israel. This stuff is all framed with wood rafters. I mean, wood rafters, and they sit on steel trusses, but they're not really attached. It's just wood. There's a bunch of wood up here. And that wood can actually slide off its supports. And in fact, actually, at the exterior walls of the building, the wood sits on corbelled brick that provides kind of the top of the arch, that forms the top of the arch. We don't want that stuff to slip off in an earthquake, because as the walls are trying to move, as the whole structure is breathing, the supports for that wood, I mean, in a lot of cases, only an inch or two of bearing. So we just simply devised some systems with wire rope. It's kind of shown schematically. These are details off our drawings, but just hanging wire rope from the roof structure to these rafters. We strengthen the roof structure. We turned what are just regular gable rafter framing by putting in, you know, a $5 piece of threaded rod. We turned that guy into a truss, and now we can hang if the ceiling were to slip off, it won't drop down, which of course, as you can imagine, if any of this stuff dropped down, I mean, you'll never get it back up. So this is just, it's kind of a belt and suspenders, but it's a good way to protect against a potential life safety problem. Parapets. Hibernia, the roof was a forest of red iron parapet bracing when we first got there. The owner, I mean, he actually wanted to repurpose the roof and use it, put it into the use of the structure and build a deck up there and everything. And this stuff was really unsightly. And it really is unsightly. Fortunately, on this particular project, we had to remove temporarily a lot of the balustrades for the purpose of putting in a concrete bond beam that held the walls together. But in the course of doing that, when we put it all back, we changed how it was supported. And the image on the right-hand side is what it looks like now, just by inserting a bunch of pins and making them seismically adequate. So, I mean, just to me, to my eye, a tremendous improvement. I always hated that stuff. I hated climbing around that stuff, and it's not pretty. Okay, last subject, hollow clay tile. There's a dilemma with hollow clay tile, of course, because we all know that it presents a hazard, right? I mean, in Loma Prieta, in San Francisco and in Oakland, I mean, tremendous damage was done to hollow clay tile. Hollow clay tile partitions fall out in stairwells. They create all sorts of secondary risks. Problem, of course, is that hollow clay tile is oftentimes the backing for character-defining features. And so we are in have a conundrum. Do we want, how much damage do we want to do for the sake of protecting occupants? Oftentimes people assume that it requires removal, but it doesn't. Nothing in the CHBC requires you to remove them. Hollow clay tile, you can, according to the San Francisco Building Code, you can mitigate it, but mitigation does not require removal. Mitigation is, in my view, is mitigation. I'll show you a couple of mitigation techniques in a minute. The City of San Francisco also only requires that HCT hazards be mitigated for egress and passersby. So you don't have to go in wholesale and mitigate every HCT problem in a building. So what are some of the ways? This is going back to Hibernia again, and if I have time, I'll show you 3 different ways that are applicable to different situations. First of all, in Hibernia, this region on the diagram that I'm showing you is region 1. All those red walls are hollow clay tile walls. Unfortunately, behind the hollow clay tile, the rooms down sheet from that wall this is one of those rooms, and actually there are 3 rooms that are very similar. I mean, my goodness, you really don't want to take those walls out, do you? I mean, you'd forever damage this thing. So we didn't. But we had to do something about them, and it was driven by City of San Francisco. By the way, and yes, I didn't say these are 2 white walls. Down at the end of this corridor, that window is going to be converted to a new exit to accommodate the new occupancy. So we really had to work. We had to do something here. This was the egress. To complicate matters, we had these very lovely metal door frames that were the same thickness as the walls. We really couldn't change the wall thickness. We had some very lovely marble tile bands. We didn't want to intrude on those things. So we developed a potentially risky means by which we said, look, if you guys can surgically remove 1 wythe of HCT, one of the 2 wythes, notice surgically remove it, that means don't get the gorillas out there, get the guys who care, and replace that wythe with cold form steel studs and run some toggle bolts from the HCT into the studs, you've now supported the wythe, the 1 wythe you want to leave. So that's exactly what we did. First, they went into those really fancy rooms and they braced the snot out of those walls and protected them. And then we went on the other side, and they surgically they didn't make a single crack in the adjoining wythe. I mean, it just phenomenal work. This can be done. Put in those steel studs, tested that the HCT toggle, the toggle anchor would work and how to install it, and ended up, we did that the whole length of this egress, if you will, and stabilized all of it. And part of it, actually, we put in a cold form steel shear wall, and also didn't intrude on the marble tile. And that was also, I think, the first use at least in the City of San Francisco of that. But in any case, this back here, that white wall that you see, I probably would have chosen a different color for it. But that white wall is the wall that we were working on. And it has exactly the same dimensions, thickness as it had when we started. We didn't intrude on the marble tile band. The doors all work fine. The door framing, all lovely. Okay, so another area in the building where there was a single wythe HCT wall was also complicated. You see this dotted red line, there are stairs. That's kind of the line of the stairs behind, which are very decorative stairs. We could easily work on this side, but we couldn't work on the back side. We had some brick walls kind of shaded behind here, and concrete. See, this is the stairs in the back side with really lovely stone wainscoting, and we just didn't want to touch it. But this single wife HCT is kind of right next to the elevator, and this is a path to stairs. This is also kind of in the egress. So we just simply, I mean, it's a simple solution, just came up with a way to put wire mesh on the face of that material, anchor the wire mesh to the HCT with these toggles again, and then on the ends, anchor the wire mesh into the brick and into the concrete on the two ends, and it just stops it all from falling out. It may well get damaged in an earthquake, but it's not going to fall on people, which is really the goal, and it left all those finishes intact, at least the nice ones on the back side. Lastly, the last solution type that I will show you pertains to these HTT walls, which are also in kind of an egress route that were single wife. Above here is the attic. This is what it looks like from the attic. These are the hollow plate tile blocks that project above the ceiling. Well, these are perfect avenues for fishing down a reinforcing rod and filling with grout. So that's what we did. You know, every 4 feet in the portion of the wall we had to, or right at the jams, we just simply fished down some reinforcement and grouted it with a low bleed grout so it didn't damage the plaster finishes. And now these things are stabilized, and we never really tore them out. And there's an image of it. And so now is the summary, which you can read it. I'll read it. The point of this talk really is that structural provisions of the CHBC provide a tremendous basis for us. I mean, this is our armor. This is our weaponry in fighting the battle of how do we preserve historic buildings. It permits preservation and seismic safety to be treated as equals, and that is exactly how they should be treated. It allows us to capitalize on historic strengths of historic structures, of inherent strengths of historic structures. But in doing so, it's important that everybody on the project team buys into the notion that it's important that we reutilize the inherent strengths in these buildings. It's a hugely important concept because it can vastly reduce the amount of intervention that would otherwise be necessary. Moreover, we should all be adopting this notion of supplement, don't supplant. It's kind of a Terry Paret shorthand, but again, it's very important. We have to be committed to targeting only critical vulnerabilities and not trying to remake the wheel when we work on historic buildings. Thank you.
Okay, we have time for some questions.
Hi, Terry. Thanks. Martin Bernstein, City of Palo Alto Historic Resources Board. You talked about the buy-in of the team members, including building officials. If the owner or owner's representative says with a qualified historic structure, we want to use the California Historic Building Code, building inspector cannot say no. Is that correct?
Well, he can say no, but he would be wrong to say no.
Okay, because the state law says that if the applicant says, I want to use this code, it has to be used, correct?
That is my understanding, yes.
Okay, good, okay. So I guess my follow-up question is that, is there any training from the state of California that the chief building officials in California know that?
It's a great question, you know, and it gets right to the heart of a problem that we all run into on our project.
The first person of the board is Dan Chudy. Dan used to be the building official. So on the other side, he gives seminars on the CHBC to Calvo. So we're finding more and more building officials, while they may be reluctant to use the CHBC, understand that they need to use the CHBC. If requested by the owner. Don't expect them to pick it for you. That's one of the things, you know, that as building owners or, you know, city representatives, you have to know that they're not necessarily going to volunteer. You need to ask for it. I have a question, Terry. First of all, how many people in the room are engineers? Okay, and how many people in the room deal with engineers? Okay. I want you to talk a little bit about why this stuff is important for non-engineers to know, especially ones who deal with engineers.
Sure. Well, given that the majority of you deal with engineers, I presume that those dealings don't always turn out the way you want them to turn out. And it's my experience, and I'm presuming yours, but if you have different ones, feel free to chime in. Engineers tend to throw out the safety card all the time, right? They tend to be pretty conservative. And it kind of goes to what I said before. You've got to get data in the engine. First, they have to be on the team. They got to, right? They got to be playing with the team, not against the team. Engineers can make projects bigger or smaller depending upon, they have a little bit of a conflict of interest, I'm sorry to say. They can make problems bigger or smaller. They can increase or reduce their own liability. There are lots of factors that go into engineers' thinking. They may not all be overt, but they're there. I promise you they are there. You need to have the right team members, and they need to understand that it's as much in their interest to have projects move forward and be successful than to have them die on the vine because they're unaffordable, or to have a product that nobody's proud of at the end. I don't know exactly how you do that, but knowing some of this stuff, and I've given a bunch of other talks on similar subjects, to some degree, engineers rely on the fact that they are rarely challenged when they throw out the safety card, because who's going to say no to safety? Right? A building official will never say no. Well, you want to add more? Sure, go add more. It's the other members of the project team that have to keep the engineers in check. And the only way you can do that is if you have some idea of what's going on and not get wowed by the terminology and wowed by the numbers. You may always be wowed by the numbers if you're not a numbers person. But a lot of this stuff can be understood conceptually. I mean, Alan himself is pretty good at this on projects and challenging engineers of why do you need to do that? What about can't we do it this way? You need to, I would suggest that you take an active, don't let the safety card trump all else, because it shouldn't, and it doesn't have to in the CHBC. The CHBC empowers us all to say, wait a minute, let's think about this. Rather than knee-jerk, oh, that's unreinforced masonry. That's old stuff. That's no good, right? That help answer your question?
I would say it's worse than that, because you're characterizing, the engineers are going, oh, that's old stuff. We're not going to pay attention to it. But the code supports that. The code pretty much tells you it's old stuff. I mean, the regular code.
The CBC.
Yeah, CBC. It tells you it's old stuff. It tells you can't assign any value to it. And if the engineer is not pretty well versed in the approaches to stabilizing a historic building, they're going to go to what they're comfortable with. And so one of the things that I would say that Terry is too discreet to say is that you have to find an engineer for a historic building that actually knows how to engineer historic buildings. They're not the same. They're not what you learn in school. And unfortunately, the things that Terry was talking about, which is reducing liability, also increases fees. So there's almost no reason that an engineer would not go to a larger, more expensive solution unless they really are trained and take great pride in their ability to analyze and reinforce historic buildings.
Great. Good points. I have a question from the people online from Scott. He's asking, it's a quick question, so maybe probably a one-word or two-word answer maybe. What's the new use for the Hibernia Bank building?
Unknown. It's not. It was designed to maximize its occupancy for use as anything. Last I've heard, there's not yet a tenant or a use selected. Yeah.
Further questions?
Isn't there a section in the code, the historic code, for archaic materials and values for those? And if
Chapter 8.
and how useful, not knowing it because I'm not an engineer, not knowing that much about it, is it something that's pretty useful for if the engineer is directed towards that? Can they make good use of it?
You can make some use of it. Some of the language in the CHBC is not all that clear, and so a lot still comes down to the engineer's intent and where they want the project to head. I guess that's all I'll say about that. I mean, there's information there, but it's certainly not. It's what, like a 2-page chapter, so it doesn't really have that many provisions in it that provide all that much guidance to a person who hasn't done that much work on these types of buildings. Yes.
2 related questions. Unreinforced brick foundations on with wood frame houses, the conventional wisdom is replace them. I'd like to get your take on what to do about them. And also unreinforced brick chimneys on wood frame buildings. What's the best way of dealing with them if the intent is to retain the chimney?
Well, I don't want to hedge too much, but obviously everything is project specific, right? There are lots of individual circumstances. It depends on whether your building is on flat ground or hilly ground, depends on whether the footings are already cracked or not cracked, or significantly damaged. I think you've got to, I don't see why there's necessarily a driving reason to replace brick foundations. Certainly not an overriding reason that trumps all else, because rarely, if ever, has anyone been killed because their brick foundation has cracked in an earthquake, right? I mean, that doesn't make your house fall. Other things make your house fall, but not cracked brick foundations. I mean, certainly not if it's just a footing. Maybe if you have a big stem wall and it's supporting a bunch of stuff out of plane. But anyway, my druthers would be to try and see if you can save it. There doesn't seem to be a big driver to take it out. Chimneys are different. I think chimneys create clear hazards to occupants of buildings and to passersby under certain circumstances. Not all chimneys. It depends on their height, on their aspect ratios. It depends how they're connected at the roof line. But chimneys, I think, do present significant potential risks, and in many instances would be much better off braced or replaced. And and depends on the actual construction. There may be some creative ways to do that are less intrusive than others.
Regarding your question about archaic materials, we did a project where the engineer actually analyzed the wood fiber of the wood that we wanted to keep. And then he also went back to the 1906 building codes to find out what was, and so we can combine his analysis of the archaic material plus the building codes in effect, and saying, here's how it's safe. And the building is still standing 100 years later, proof that it's safe. Here's our archaic material data. So going back to the old codes was a great research tool.
Question back here.
Thank you for your presentation. I'm a non-engineer, so it's refreshing to attend a class where it's not all based on formulas. There's one thing that you didn't go over, which was the elastic cables that were used, that the 60-foot dome was helping to support the walls. Could you please expand on that?
I'm sure. I'm happy to. So we used a material called nitinol, which is a nickel titanium alloy that really, it was discovered, I don't know, in the 30s or 40s, I think, by the good folks in the Navy. And people have been seeking out uses for it for decades. Its primary use now is actually in the medical industry. This is a boutique metal. It's like it's nickel, titanium. It's boutique-y. It's fabricated can be to some very detailed specifications. It's used for stents. It's used for for eyeglasses, for all sorts of medical stuff. It's only been used prior to our use in seismic applications, to my knowledge, in Italy, in 3 medieval cathedrals that were damaged in the Assisi earthquake. In Europe, in Italy, they used it in a very expensive manner. But let me first describe what this stuff is and why it's so special. So this stuff is as strong as steel, strong as most steel, stronger than some steels, but it's very elastic. So if you were to take, for example, a 100-inch length of this stuff and stretch it 6 inches and let go of it, it would come back to 100 inches. It kind of makes you go, ugh, you know. I mean, it's mind-boggling stuff. It's mind-boggling, and it has other interesting properties that I'm not. It has kind of it has shape memory, which means that if you were to pull it much beyond those 6 inches, it would stay put. If you pulled it to 110 inches, it would probably, I mean, depending on the specific alloy and working of it, it would come back to 104 inches, right? It's 110 minus 106 is, or minus 6, it would come back to, it would be stretched 4 inches. If you then heated it up, it would then go point and come back to 100 inches. Anyway, it's pretty cool stuff, and we used it in a way that was very inexpensive. On Shareth Israel, the entire, all the purchase of nitinol, I think, cost about $5,000. And actually anchoring it was more expensive than the material itself. You know, it's come down way in price. I can talk about what allows the wall to do it. Sorry, if that helps. So the theorem is really that during an earthquake, when the gable walls, when everything's swaying back and forth, you know how gable and how these kinds of walls ultimately fail is they get cracked, and then each cycle of the earthquake, and the cracks kind of form large sections of masonry, right? Really large sections. And each cycle of the earthquake, as the walls sway, those sections start to walk out of position, and eventually they fall out in the street. You know, they get unstable, they fall out in the street. What the nitinol is there to do is when each cycle reverses, when the motion of the walls reverse, even if the nitinol kind of was forced to stretch way out of position when the walls tried to move outward, when the walls then start to sway inward, the nitinol is exerting a very positive force on it. It says, okay, come back in, as opposed to steel, which would never do that. If you use steel, once it moved out, it's out. In fact, then the steel is going to resist inward motion. So it's working against you. In this case, the nitinol works for you because it kind of pulls it, trying to pull it back. I mean, I'm not saying that's going to be a successful strategy that will actually keep them in their original position. Probably won't, but at least it's a restoring force of sorts, and it wasn't a big cost margin.
So your implementation and your alternatives were so innovative and impressive. But I'm not an engineer, so I don't know if they're conventional, which brings me to my question. If we're saving costs by using these innovations in your projects, do we increase costs over time in terms of repair and maintenance if we use unconventional materials or principles?
It's a good question, and I think my answer is there's nothing cheap about fixing a cracked reinforced concrete wall or fixing yielded steel moment frames or buckled braces. I mean, repairing damage costs money. I don't see that. I mean, for example, the nitinol, if it's damaged, all of those wires, 100% of them can be replaced. It's a $5,000 cost. I mean, that's pretty cheap. Now, I think the bigger component of damage will be the masonry will be cracked in a lot of places. but there's no solution you can put in place, traditional or otherwise, that's going to prevent your masonry from cracking to some degree in an earthquake, right? I mean, that's not even the goal of the CHBC. It's certainly not an explicit goal. We're just trying to protect life safety. So earthquake damage is kind of, it is explicitly expected. You know, I'll tell you, for just so it's clear, the design of brand new buildings today, not all that well publicized, but when you design, the engineering profession has decided that the criteria for the design of brand new buildings will result in a pretty high probability of collapse in a major earthquake event, that high enough that I think people would be shocked to know what it is. That actually presume that if you design a brand new building to today's code, that there's a 10% chance of collapse if you get the maximum considered earthquake. That's a pretty high probability. And every building up to that, you know, that doesn't collapse is going to get damaged. So even, you know, kind of very traditional building designs are all, it's all baked into the cake, this expectation that we're going to have a lot of damage and there's going to be a lot of cost associated with repairing that damage. I don't see that these methods are changing that measurably.
Okay, I hate to move us on, but we are running a few minutes late, not too much. There was a very vigorous Q&A period here. So I'm going to get us moved on, but I'm going to turn it over to Helen to introduce our next speaker.